Alright, in this video we're going to do an introduction to ordinary differential equations. So here we'll look at definitions and notation to do with ordinary differential equations. So first thing we're going to do is we're going to define an ordinary differential equation. So ordinary differential equation is an equation that involves an unknown function, for instance y, and this unknown function is a function of one variable, which is your independent variable, could be x for instance. And then in this equation we are also going to have the derivatives of the unknown function plus its derivatives. Okay, so that is an ODE. The one here is important. This is what makes this an ordinary differential equation. So this is a function of only one variable x, then this is an ordinary differential equation. If it's a function of two variables, for instance x and t, then this becomes a partial differential equation, which we're going to look at in another video. So some examples of ordinary differential equations: dy dx minus 2y is equal to e to the x is an ODE. Also y triple prime plus y prime is 2x squared. That's an ODE. X squared y, fourth derivative of y, minus 2xy double prime plus y equals to 0. And lastly, x double dot minus 4x squared is equal to 0. Now, so in each case, there is an independent variable and a dependent variable plus its derivatives. In A, the dependent variable is y, independent variable is x. It's always the variable with respect to which we differentiate. In B is the same situation. In C, same situation. In D, the dot notation means derivative with respect to t. So the independent variable in D is t, the dependent variable is x. Now, the order of an ODE is the highest derivative that appears in the ODE. This is the highest derivative that appears in the ODE. So that is the order. And then the is also homogeneity. So an ODE is called homogeneous if all the terms involve the dependent variable. Okay, the dependent variable. So maybe let's just look at the examples we have above. Dependent variable. So let's start with order. So we're going to look at the orders of A, B, and C. So we're saying the order is the highest derivative that appears in the ODE. So for the first one, the highest derivative is 1. So the order of this ODE is 1. For B, the highest derivative, we have got y prime and y triple prime. Highest one is 3. And for C, we've got second order derivative and fourth order derivative. So that's an ODE of order 4. Here we have got x double dot, so that's a second order derivative. And then an ODE is homogeneous. All the terms involve the dependent variable. So in A, dependent variable is y. That's the derivative of y there. That's y there. There's no y there. So that means B is non-homogeneous. Okay. Then for B, we have got y here, y there. There's no y there, so this one is also non-homogeneous. For C, we have got y here, y there, and y there. So that one is homogeneous. And for D, remember the dependent variable is x. Got x here and here. So that one is also homogeneous. So that's a homogeneity in this column. Okay, then the next property is linearity. So an ODE is called linear if it is linear in the dependent variable and its derivatives. Okay, what this means is that each of the terms involving the dependent variable occurs to the power 1 or its derivatives to the power 1, and they don't multiply each other, so no dependent variable terms multiply each other. So for instance, in A, so we're going to have linearity here. In A, so that is linear because that's y to the power 1. That's y prime to the power 1. So this one is going to be linear. Okay. Second ODE, this term is linear. This term is non-linear because we've got a first order times y. So that one is going to be non-linear on account of the second term. The third equation, this term is linear. This term is linear even though it's multiplied by x, but the dependent variable terms do not count in terms of linearity. This is also linear. So that equation is linear. And then the last one, the first term is linear, but the second term is non-linear because this is a quadratic term in x, which is the dependent variable in this case. So that is non-linear. All right, so that is order, homogeneity, and linearity. The next thing we're going to look at is the definition of a solution. Okay, so a function is called a solution. of an ODE, if it satisfies the ODE in the given domain, if it satisfies the ODE. Okay, so as an example, y equal to ae to the power 2x minus e to the power x, okay, where a is an arbitrary constant. This is a solution of the first ODE that we have above, which is dy dx minus 2y is equals to e to the x. So this one is a solution. This is an unknown constant. It comes from integration. So a solution that involves an integration constant, one or many, is called a general solution. So in fact, this here is the general solution of this equation here. So the general solution of a first order ODE is going to have one unknown constant because we integrate once. General solution of a second order ODE is going to have two unknown constants, etc. So the number of constants is always going to correspond with the order of the ODE. So this one in particular, because it's got only one constant, this one is called a one parameter family of curves. Okay, this is called a one parameter family of curves. So for each value of a, we're going to have a curve corresponding to the solution here. Let's just have a quick look at how these curves look. So we're going to start with this one here. So a is 1, and you can see this is how it looks. Actually goes through the origin, because when x is 0, y is also 0. If a is 2, then it's going to look like this one. It's got y-intercept 1. If a is 3, y-intercept is 2, etc. But a could be negative as well. If a is negative 1, it's going to look like this curve here, y-intercept negative 2. If a is negative 2, then the y-intercept is negative 3, etc. So this is going to be the shape of the one parameter family of curves for that ODE in A. Alright, so that is the idea of a general solution. Now, out of these many solutions here, sometimes it is required just to find one of them, in which case then we say we require a particular solution. Okay, so if a particular solution is required, then extra data is given over and above the ODE, and that extra data can either be named an initial conditions or boundary condition. Okay, so let's see how this works out. So a particular solution is a solution that satisfies a given condition, okay, that satisfies a given condition. A given condition. For instance, in our case here, we could say find the solution going through, say, 0, -5. Okay, see this last one here goes through -4. Suppose the one that goes through 0, -5, then that would be a particular solution. Now, the given conditions are called initial conditions if they are given at one point. Okay, so initial conditions I see. So these are all given at one point, either in time or in space. Then boundary conditions. So conditions are called boundary if they're given at different points. Okay, so this is boundary condition given at different points. Okay, so let's consider a particular case of the ODEA. So dy dx minus 2y is equals to e to the x. Suppose we want a solution which is such that when x equals to 0, y is -5. Okay, so what we do here is we go to this general solution here, and then we plug in x is 0 and y is -5. So that means we're going to have -5 here, 0 here, and 0 there. So we're going to have -5 is a e to the 0 minus e to the 0. This is going to give us a is -4. So the particular solution is going to be -4e to the 2x minus e to the x. So this is a particular solution satisfying that initial condition. All right, so that's the idea of what an ODE is, the order of an ODE, the linearity, the homogeneity. We have now defined a solution, a general solution, a particular solution, initial conditions, boundary conditions. So let's just look at an example of a system which has got boundary conditions. Okay, so this is another example too. Let's say so if we've got the ODE x double dot plus 4x equals to 0. This is the second order ODE. The general solution of this so this ODE has the general solution a cosine 2t plus b sine 2t. So this one is our general solution, where a and b are arbitrary constants. We could find a particular solution if we specify conditions, so there have got to be two conditions because we got two unknowns. So suppose we say when t is 0, x must be 2, and we say at the same time when t is pi over 8, x must be 0. So in mechanics, if x is the displacement, then x dot is the velocity. So this is specifying the velocity at time t equals to 0, and specifying the displacement, and then the velocity at time is t is pound 8. So this is a boundary condition thing, because we're specifying these at two different times, and so this whole thing is called a boundary value problem. Okay, so this is a boundary value problem. The whole system is called a boundary value problem, abbreviated BVP. Particular solution of this one is going to be x equals to 2 into cosine 2t plus sine 2t. You might want to confirm this. All right, so we're going to end it here. Thanks for watching this video. In the next video, we're going to start looking at well, if you're given a solution, can you find the ODE satisfied by that general solution?